In this segment, I'm going to start talking about Chapter 16. And Chapter 16 is one of my favorite chapters in this entire book. We cover some really cool stuff. This is all about how waves combine. And this is a chapter where we're going to see some surprising stuff. My favorite moments in physics is when our common sense goes this way, but reality goes this way. And at that point, we're faced with something in our brain. It's called cognitive dissonance, right? My common sense tells me this is right, but logic tells me this is right. And we have to resolve that. We have to find a way to resolve that. And there's such cool stuff in this chapter. So we're going to talk about standing waves and superposition. Superposition is simply a fancy word for how waves combine. In this chapter and in some subsequent chapters, when we start talking about light, we're going to encounter some very surprising things about the ways that waves combine. But just a quick example of standing waves. Well, I've already demonstrated this in a previous segment. This is my PVC pipe, which I can make a note on. We can think of that as a standing sound wave inside this tube. I might even be able to make a different note. Beautiful, isn't it? Oh. Probably not going to get a job in the symphony with that one. I can make a couple different notes in there, but I can only create notes that correspond to standing sound waves in this tube. We'll talk more about that in a minute. Ooh, that one's a little prettier. Smaller pipe, higher pitch. Bigger pipe, lower pitch. Shorter standing wave, longer standing wave. We'll get into more of that in a minute. The easiest standing wave to demonstrate is the wave on the spring. I can send a traveling wave down this spring, and we all get the sense that something's going down and back. But I can also set up a standing wave. I suspect you've lost that sense that something is traveling down and back. Yeah, there's something very wavy about this, isn't there? And so we can set up a couple of different patterns here. We can set up, I call this the one lumper, but I could also create the two lumper. Oh, maybe that's the three lumper. I can create the two lumper. Oh, there we go. Lovely. Again, very wave-like. It is a wave. It's a standing wave. It's not a traveling wave. We don't get the sense that it's going somewhere, right? I might be able to create the three lumper here. Let's see. Oh, beautiful. Beautiful. Oh, I love it. All right, so those are different standing waves on a spring. We're going to get into more of that here in a little bit. First, let's talk a little bit about superposition of waves. So again, superposition is just this fancy word, and it means waves combining. How do we combine waves? How do waves add or sometimes subtract? So to say it fancily, when two or more waves are simultaneously present at a single point in space, the displacement of the medium at that point is the sum of the displacements due to each individual wave. Superposition is how waves combine. But this says it's the sum of the displacements. That is an important point. Notice here we've got two waves that are going to combine. What's the amplitude of this wave? Oh, I don't know. It's this far, right? It's not very big. This is a fairly small wave. When the two waves combine, we get a much larger amplitude. We can think of this as one wave going this way and one wave going this way. They combine, and then they pass, right? And notice, after they've passed each other, they just continue on their merry way. This is how waves combine. The amplitudes add. And we can see that sometimes that's a little bit surprising. I don't think anyone's too surprised quite yet. So here I'm going to show a couple of waves, and these are goofy looking waves, aren't they? One is a square wave, one's triangular shaped. You know, we talk mostly about sine waves, and things like, you know, a note, la, like that is, it's basically a sine wave. And so why am I using triangles and rectangles here? Why? Because I can really see how they add. And so this is not necessarily a realistic wave, but it's realistically how waves add. And because I'm using a triangle and a rectangle, we can just see how they add a little bit better. So here we're going to see some snapshots as these waves approach each other. We've got a triangular wave moving to the right and a rectangular wave moving to the left. Here they're just about to combine. And here they have combined. And now we have two waves adding, right? When the amplitudes combine and they're in the same direction, we call this constructive interference. And here we see that we have just added the two waves. This is another picture showing constructive interference. These two waves add. We'll talk about a different kind of interference here in just a second. So here we see constructive interference, and this occurs when both waves are positive. And so the total displacement of the medium is larger than it would be for either wave separately. Again, both of these waves are moving towards each other. Again, this is a snapshot. We're continuing these pictures over. They're moving towards each other. They're just about to meet, and now they have met. These dashed lines represent what the two individual waves are. This solid line represents what the sum or the superposition of the two waves looks like. Now they just continue on their merry way. 1 second later, the triangular wave is just about to leave. Again, we see the triangular shape here, the rectangular shape here. When we add them together, we get this goofy shape. And now they've passed each other, and they keep on going. Again, this is an example of constructive interference because both displacements are positive, and so those two waves add. Now, destructive interference happens when the displacements are in opposite directions, when one has a positive displacement and one has a negative displacement. And so we see that waves can combine to make a greater amplitude. Interestingly, waves can also combine to make a smaller amplitude. So destructive interference is when the displacement of the medium where the waves overlap is less than it would be due to either of the waves separately. And so what that means is basically you've got one with a positive displacement and one wave with a negative displacement, and then they combine, right? And so here again we're seeing some snapshots of some waves overlapping, and here we see they're coming towards each other. Oh, they've just started to overlap, and when they're right on top of each other, they cancel each other out. Notice these dashed lines are what the two waves are. When we add a triangle up to a triangle down, they completely cancel out. And now here they are passing on, and they're moving on. You know, some people say, how does this jive with like conservation of energy or something, right? Doesn't this wave carry energy? And in this snapshot right here, there is no energy. And the answer is that energy is stored in the kinetic energy of the medium. It's a little bit weird, but it's true. This is a video produced by Pearson, the publisher of our textbook. This is Brian Jones, one of the authors of our textbook. So that was a great example of destructive interference. It seems so counterintuitive at first, that two waves could combine to create a wave with no amplitude. But we just saw that happening, right? We saw one wave coming from the right and one from the left. Where they met in the middle, the amplitude canceled. And we saw evidence of that because they did not knock the cups over. So, pretty cool phenomena. There's all kinds of applications out there, lest you think that this is just some made-up thing for physics class. This is how your noise-canceling headphones work. It turns out that your noise-canceling headphones create a sound wave that is exactly the opposite of the sound that it's hearing from outside. So your noise-canceling headphones make it quieter inside your headphones by creating a sound wave. That sound wave is perfectly inverted from the sound that's coming into your ears, and so it cancels out with it. It creates destructive interference. Pretty interesting stuff. Let's do a quick example. Here we see two wave pulses on a string. They're approaching each other at speeds of 1 meter per second. How does the string look at 3 seconds? Well, why don't you go ahead and, you're going to want to probably draw this one out. I'll see you on the other side. Okay, well here I've drawn out my original configuration. Let's see where these waves will be in 3 seconds. So this guy here, he will be, let's see, in 3 seconds it'll be 1, 2, 3. He'll be right here. And 1, 2, 3. Oh, these guys will overlap, won't they? So there's my 2 original waves. What happens when I add those together? Well, I will end up with something like this. Kind of ran out of room here a little bit, but we get the idea. We're going to end up with something like that. The correct answer is C. This is an example of constructive interference.